Good morning, everyone. Good morning. We are very delighted to have Professor P.R. Kumar from Texas University, A&M University with us today as our distinguished colloquium speaker. As you know, this year is also very auspicious for us. It's the 150th anniversary of Missouri S&T. So a lot of activities are going on. So in our department, we are having several distinguished colloquium speakers, and we are dedicating towards that celebration as well. And Professor P.R. Kumar is with the Department of Electrical and Computer Engineering at Texas A&M University. He is a Regents Professor, University Distinguished Professor, as well as the holder of the O'Donnell Foundation Chair 1. Previously, he was a distinguished endowed chairholder, emeritus now with the Department of Electrical and Computer Engineering at University of Illinois at Urbana-Champaign. He is also an honorary professor of IIT Hyderabad. His contributions in computer science, engineering, electrical engineering, networking is a lot of contributions. He has made a lot of foundational work, and many of you probably know some of the famous work that I know in networking is Gupta and Kumar's theory for capacity analysis of mobile ad hoc networks. He has done a lot of things on the control systems as well. His accolades and number of awards is too many, and you have actually seen his bio, so I'll not take too much time to enumerate all of them, but he is IEEE Field Award holder for computer system control systems, as well as the Donald Ekman Award for the American Automatic Control Council. He has got Test of the Time Award from ACM SIGMobile, the mobile special interest group, as well as the Infocom Achievement Award. He is a member of the National Academy of Engineering in the US, as well as the Academy of Medicine, Engineering and Science of Texas. He's an IEEE fellow, an ACM fellow as well. And he got his PhD degree from University of Washington in St. Louis. So in that sense, actually, he's very much familiar with this area as such. So without much ado, let us welcome Professor Kumar. Thank you, Professor Kumar, for agreeing to speak to us. We are all eager to listen to you. Please, so podium is yours.
Thank you very much. So first, thank you, Sajal, for this opportunity to visit Missouri. I wish it had been in person. It would have brought me home after a few decades, but we'll have to do that some other time. So let me put screen share, I guess the slideshow, and please let me know if the slideshow works. Is it visible, the slideshow?
It is, yeah.
Okay. So, so I'm going to be talking about the security of cyber-physical systems and the theory for this. And a lot of the work is in the thesis of Bharadwaj Sachidanandan, who graduated from here a couple of years ago and is now a postdoc at MIT. And of course, all the work is done by the postdocs and students. Wu Hyun Ko is a postdoc who did his PhD with me earlier. Gopal Kamath was visiting as a postdoc from IIT Madras. Jaewon Kim is my PhD student. And Tong Hong, Lang Tian, Shang Wan, Kenny Chur are all PhD students at A&M. Okay, so, oops, excuse me. Okay, so what are cyber-physical systems? I think most of you have heard this phrase. These are systems in which computing, communication, control are very tightly integrated. And you could say this is the outgrowth of all the research that has been done in networking, communication, control, signal processing, computation over the past 6 decades. Now, many societally important future applications are going to be large deployments of cyber-physical systems. Examples are the smart grid, automated transportation, unmanned air vehicle transportation systems, water treatment facilities, telesurgery systems, etc. Now, many of these systems are safety critical. What that means is that if they malfunction, it can actually end up causing physical harm. And they are critical infrastructure because they're very important for the functioning of the economy and the society. Yet they are vulnerable to cyber attacks. In fact, traditionally in networks, hackers can only tamper with the information bits in the cyber layer. But because CPS couples the cyber and the physical worlds, the actions taken in the physical world are based on the information from the cyber layer. And therefore, in cyber physical systems, hackers can actually cause physical damage. You cannot just play around with bits, but actually cause physical damage. And in fact, there have been several attacks on critical infrastructure systems, sewage treatment plant in Australia, a nuclear power plant in Ohio. A very well-known example is the Stuxnet worm. There have been attacks on SCADA systems and many, many more instances of attacks. A recent example is attack on the Ukrainian power grid, etc. Now, one question that people ask is, hey, isn't networking security already enough for cyber physical system security? And the answer is not, no, because typically this networking information security is implemented through periodic patches. They ask you to reboot your system. But in CPS, which has a dynamic system in the loop, you cannot keep rebooting it, for example, a power system. Also, traditional notions such as confidentiality, integrity, availability, they don't really address real-time systems. And that's very important for control system security. But more broadly, the whole cyber physical system opens up a whole physical layer attacks beyond just information layer, beyond just the cyber layer. So we need to look at this problem afresh. Okay, so to summarize, many societally critical systems are being networked. They are safety and economy critical. Malfunctioning can cause physical, economic, or physical harm. There have been attacks. Now, the question is, even after many decades, we still cannot secure operating systems. Every day I get a patch from operating system saying, hey, listen, time to update your operating system. Every day we get a patch for the internet. So if you can't secure operating systems in the internet, how can we secure cyber physical systems, which have an even more layers of complexity? Okay, and what I want to show you is that actually you can do this in a strange way. It's actually simpler than securing just the cyber infrastructure. Okay, the key to understanding how to do this is the right abstraction for cyber physical systems. So the overall cyber physical system is as follows. There is a physical plant at the core. That physical plant could be the smart grid. It could be an autonomous vehicle. It could be a chemical oil refinery, whatever. And this physical plant has actuators. For example, in a car, your actuator is your gas pedal or your steering wheel. And it has sensors. And these sensors measure the outputs of the physical plant. For example, the velocity or position, etc. Okay, and the loop is closed between the sensors and the actuators, the control loop, possibly over a communication and information processing network. Now, this network could consist of, say, dumb routers, but it could also contain computational nodes which fuse information. Okay. All right. Now, the issue is that some of these nodes could be compromised. For example, some of the sensors could be compromised, or some of the routers or information processing units in the feedback loop could be compromised. And the question then is, how can we secure the overall cyber physical system when these nodes are compromised? Today, I'm not going to be talking about the case where the actuators are compromised, though we have theories for that. We're going to be talking of the case where either a sensor node could be compromised, which means that you don't get access so the true sensor readings are not reported back to you. Only false readings are reported. For example, somebody may be telling you the wrong velocity of your vehicle or the wrong position, or it could also be that the sensor is not compromised, but the information is compromised somewhere along the way. So by the time it reaches you, the information is wrong. Okay. All right. So we're going to abstract this overall physical system as follows. We'll just consider a physical system with sensors and actuators and simply suppose that either some of the sensors could have been compromised or some of the actuators could have been compromised. Now, as I said, we're going to focus on the case where the sensor is compromised. And when I say the sensor is compromised, I also include the case where the sensor information is compromised somewhere along the route. So if the information from a sensor is compromised anywhere, we simply regard the sensor as compromised. So that's a very simple abstraction, okay? And it doesn't matter where the information is compromised. So in that sense, we can even handle attacks on the network. And the question is, how do we secure the overall cyber physical system when some sensors and actuators may be compromised? And I'm going to pay particular attention to the case where only the sensors are compromised today. All right, the basic technique we're going to use is called dynamic watermarking, and it's actually very simple. So what is a watermark? If you take a sheet of paper and expose it to the sunlight, you will see that there is an indelible mark in the paper, and that's a watermark. And this watermark cannot actually be removed from the paper, okay, without destroying it. Okay, so we have a physical system here. And let us say these are the sensors. They're measuring various outputs of the physical system. And let us suppose that the actual sensor measurements are y of t. So y of t is a vector, the vector of actual measurements. But let us suppose that some of the sensors have been compromised. And what they actually report is a vector z of t, which may be different from y of t. So z is what you are told the sensor readings are, which may be false, where y is the actual truth. Now, these reported sensor measurements are then fed back over the network to the actuator, and the actuator chooses an input based on the reported sensor measurements. So the actuator faithfully follows up using the control law corresponding to the reported measurements, which, however, could be false. Now, the basic technique that we'll use of dynamic watermarking is very simple. We are going to superimpose a private excitation onto the nominal actuator inputs. So we're going to add, if you like, a small, let us say, white noise or small private random signal onto the control inputs. Okay, I'm going to call that signal as EI of t. This is the random signal imposed at the ith actuator. And we're going to call this signal as a watermark. Now, this watermark is secret. What I mean by secret is that I can tell you that I'm going to apply a watermark. I can also tell you the statistics of the watermark. But what is secret is actual waveform. So I'll tell you that I'm applying a watermark, but I won't disclose the actual waveform. Okay. Now, how does that protect the system? Okay. So net input is a combination of what you're supposed to apply plus the secret watermark. Okay, so why does that help? Well, you apply a watermark into the actuator, and this watermark percolates through the physical system, right? So it's like a indelible signal that has been injected into the system. It enters, it goes all over the system, okay? And in particular, it shows up at the sensors. Now, the sensors report their measurements back to you. And then, so therefore, these sensed measurements should contain the watermark that you applied appropriately transformed. For example, if there's a transfer function from input to output, the watermark also should be transformed by that transfer function. So what we can do is we can compare the returned signal with the secret watermark that we applied and build an attack detector. And this attack detector can tell you whether the sensor measurements have been compromised. Okay. Now, I should add one more comment here. All I'm going to be talking about is detection of an attack. The next question is, after an attack has been detected, what should you do? What is recourse? Well, that depends on the context. For example, if it is a car on a deserted highway, then you can just stop the car, pull off the road and stop the car. But if you're in a plane or in a drone, you cannot just stop it. You have to find some safe place to land. If you're in a chemical oil refinery, maybe you'll switch off the automatic control loop and go to manual operator control. Or if you're in a power system, maybe you'll check a team out. You'll send a team out to check whether if some sensor is working. So what you do depends on the context, and I'm not going to get into that. My only goal here is to detect an attack as quickly as you can, as soon as it happens. Okay. All right. Let me take an example. So if you understand this very simple first order single input, single output system, you'll get a very good insight into this whole technique. Okay. So let's take a simple system which has one input u of t and one state, which is also the output x. Okay. And there's a simple linear dynamics between the input and the state. So tomorrow's state or measurement or output is today's state multiplied by A plus today's input multiplied by B. In addition, there is always ambient noise in the system. So W is some random noise which is present in the system. And for the purpose of this example, let us suppose that this ambient noise is a Gaussian noise with mean 0. And importantly, let us suppose that its variance is sigma squared W. So this is the variance of the ambient noise in the system. Now, what do we do when we do watermarking? This input, we're going to take the nominal input that we are supposed to apply based on the reported measurement, plus we apply a secret random watermark. So the input is the superposition of two inputs, the nominal control input plus a secret watermark. And we'll suppose that the secret watermark is also, in this example, a Gaussian, white Gaussian noise with mean 0 and variance sigma squared E. So it's important to remember two quantities here. Sigma squared W is the variance of the ambient noise already present in the system. And E is the variance of the watermark. Sigma squared E is the variance of the watermark that you deliberately inject into the system. Now, if you take this input and substitute it into the system equation, you'll get xt plus 1 is axt plus beut. But u is ug plus e. So you'll get bug plus be plus noise. So this is the closed loop system containing the watermark as well as the control law. Now I'm going to take this equation and I'm going to write it in two different ways. This exact same equation is written in two ways. In the first way, I'm just going to retain W on the right-hand side and move everything else over to the left-hand side. And in the second equation, I'm going to retain W plus BE on the right-hand side and move everything else over to the left-hand side. Now notice that W is a Gaussian signal with mean 0 and variance sigma squared W, which means this left-hand side should also have variance sigma squared W. Okay. Now, however, you don't know X because these are the actual sensor measurements that you may not have access to. You only have reported sensor measurements. So you can replace X by the reported sensor measurements, which let us say are Z. So you take ZT plus 1 minus AZT. And then you know what control law you've applied. You also know the watermark you've applied. So you can construct the version of this left-hand side based on reported sensor measurements and check whether it has a variance sigma squared W. Okay, so that's one of the things we'll do. Now, secondly, we can also write this equation in such a way that we retain BE plus W on the right-hand side and everything else on the left-hand side. Now, in this case, E and W are independent Gaussian noises. So their variance is the sum of the variances. So the variance of this right-hand side is sigma squared W plus B squared sigma squared E. So you can do one more test. You can take a reported sensor measurements and use this left-hand side and check whether it has this variance. So those are the two tests that the actuator is going to conduct. It will take the reported measurement ZT plus 1, subtract AZT, subtract BUGT, subtract BET, and it will take the sample variance of that and check whether it is sigma squared W. Then it will again check for this equation. It will take ZT plus 1 minus AZ minus BUG and check whether it has a variance, sample variance, B squared sigma squared E plus sigma squared W. This is what the attack detector consists of. And if either test fails, then clearly there is something strange, malicious going on, right? Because if the reported sensor measurements were correct, then they should satisfy these equations. But if they fail, then it's clearly something going on, okay? And what do you do if it fails? Well, that recourse I'm not going to address here. The system somehow goes into a safety mode. It could be halted, it could be rebooted, it could go into manual operation, etc. So the point is that this is necessary condition for the system to not be under attack. In other words, if it fails these tests, then the system is under attack. The more difficult question is supposing the tests are passed, supposing these check out correctly, then can you give a guarantee that there is no attack? And that's the heart of the theory, which I'm not going to explain. It's a non-trivial proof. What we can show is that if the tests are passed, then essentially the system cannot be under attack. And I'll quantify that in a second. Okay. So in that sense, this covers all attacks on the system. Okay, the attacks can be as Byzantine as you like. It doesn't matter. Okay. So this is the fundamental guarantee provided by dynamic watermarking. This is the theorem. Let us define the signal V. I'll explain what this V is in a second. Define the signal V. Then the fundamental theorem is that V has zero power. Power is the mean square average, value of V. And the theorem simply says V has zero power. How can we interpret this theorem? If you reorganize the equation for V, you'll see that ZT plus 1 minus AZT minus BUG minus BE is W plus V. That's what this equation is. Now, Z are the reported measurements. So what this equation is saying is that the measurements that have been reported to you follow the same dynamic equations as the true measurements. In fact, if V were not there, this would be exactly the equation followed by the true measurements. But what we're saying is that there could be an additional V here, which, however, is restricted to zero power. So what this means is that the reported sensor measurements reported by the malicious attacker can at best distort the actual noise present in the system. This is the noise present in the system by adding to it a zero power signal. So all that the attacker can do is add a zero power signal to the already present ambient noise in the system. Okay. Now, from that fundamental result, you can actually give a lot of other guarantees. For example, if you have a system that's open loop stable and you're controlling it, then you can show that the distortion caused by the sensor is zero power. You can also show that the mean square performance that you think is happening is actually the truth. And if you are applying a stabilizing norm and stabilizing control law, then the system is stable, etc. So a lot of other results will follow from that fundamental consequence. Okay, and in fact, these results, the simple example, can be generalized to much more general situations. For example, it can be generalized to autoregressive moving average systems with exogenous inputs. These are the bread and butter models for process control systems, for example, or your chemical oil refineries, etc., or to multi-input, multi-output, partially observed systems, which are the bread and butter models for electromechanical systems in aerospace and so on. Okay. Okay.
Professor Kumar, may I ask a quick question?
Absolutely.
So the thing that you presented so far, it is for IID, right?
I gave an example where the noise was IID, where the ambient noise was IID, and I injected an IID watermark. Yes.
So the theory that you presented so far is for IID, right?
No, the theory extends to, so in RMAC systems, this is what is called colored noise.
Okay.
So this is the shaping filter of the spectrum. So it can be applied to non-IID noise also.
Okay.
Okay, yeah. But the simple example I gave you was just IID. Okay, just to understand the context. Okay, let's take an example. And in fact, this also is IID noise example. So this is a kind of a canonical system that you find in process control systems. The moving average of the output is like a moving average of the input plus noise. And in this case, I've taken white noise, but you could add colored noise over here. And let us suppose that this noise is variance 1. Okay. Now, let us say that we are doing minimum variance control. In a lot of chemical processes, the goal is to keep the fluctuation of the process as small as possible. For example, if you're making paper in a paper mill, you want to keep the fluctuation of the paper thickness as small as possible. Or if you're doing level control of a tank, a fluid in a tank, then you want to keep the level as close to the nominal level as possible. So people do what is called minimum variance control, and this is actually the minimum variance control law. Now, however, the actuator is applying the minimum variance control law to the reported measurements, which could be false. Okay. And the actuator applies a watermark. Now, the closed loop system, after you take this input and apply it over here, it becomes a mixture of the output becomes a combination of the true output, the reported output, the watermark, and the ambient noise. Okay. Now, the attacker doesn't know what your watermark is because it is secret, but the attacker could do something. He could do an estimate of it. He could estimate what the watermark is based on the measurements of Y and Z. Because the attacker can observe the true measurements and also the reported, he of course knows what the reported measurements are. He can estimate the noise, and he can do, add fake noise to the measurements so that statistically it looks the same. Okay. All right. Now, by the way, this is a more sophisticated attack than, for example, the Stuxnet attack. The Stuxnet attack simply took yesterday's, I'm colloquializing it, took yesterday's recorded measurements and replayed them today, saying these are today's measurements. Okay. So this is a more sophisticated approach. And in the absence of watermarking, the actuator wouldn't suspect that there are malicious measurements. Okay. But the attack detector catches the attack instantly. So this attack on the sensor begins at this time, and immediately the actuator test raises an alarm and tells you that the system is under attack. Okay. Okay, so this is just a simple textbook kind of example. Now, before I go into practical implementations and so on, I just want to address some theoretical questions. For example, do we really need both tests? And it turns out you do. So this is an example which of an attack which passes test 1 but fails test 2. And then here's another attack on a system which passes test 2 but fails test 1. And in fact, you need both to give these guarantees. Okay. The theory also can be extended to non-Gaussian noise and things like that, which I'm not going to get into. Okay. Okay. Let me get into implementations now. Okay. So the first implementation I'm going to show you is something we did in our laboratory. We have a laboratory autonomous transportation system. And so a CPS lab, it has all these radio controlled cars. And then we have both sensors consisting of video cameras as well as Vicon system for positioning. You can use whichever you like. And then we have all these laptops which are doing feedback control. So it's a complete closed loop system, closed over cars, over laptops, over networking, over sensors, etc. Okay. And in fact, in this particular example, we are going to attack an already smart transportation system. And this system is smart in the sense that it automatically has collision avoidance built in. So if you take a human car and drive through this automated system, the automated cars will try to avoid collisions. Okay. So it's a collision avoidance system built in. But even the collision avoidance system can be attacked if you attack the sensors. So if you get wrong information in the system, then even your collision avoidance system cannot protect you. So that's the video that you're going to see. So these are the equations of the kinematic equations of the vehicles. There are some details about sampling speeds, etc. And now, first thing I want to show you is, I'm going to show you the performance of the system in the presence of the watermark and in the absence of the watermark. So there are two curves here, one in blue and one in red, and they almost coincide. Basically, the performance of the system is almost the same to the naked eye with and without watermarking. So watermarking doesn't really adversely affect normal operation. Now, this is something that people are always concerned about. You don't want to add something to a system which degenerates the normal operation. And this one shows that it doesn't. Okay, so the watermark doesn't result in any added penalty on performance. Okay, now we do a bias attack on a sensor. Okay, and this particular test actually passes test 2 but fails test 1. And you can see that it fails test 1 because you can, those sample variance tests, I presented them as asymptotic tests. You can easily convert them to statistical tests with some thresholds. So the sensor attack begins at this time and it gets caught when it passes the 3 sigma level. Okay. And test 2, however, passes. Okay. I'm going to show you a movie of this now. So this is a smart transportation system, and the human-driven car, the automated cars avoid collisions. So you can see the second car is doing a little bit of a drunkard's walk and ultimately collides. So the point is that there's actually nothing much to see. When you use dynamic watermarking, it catches the attack and stops it. So I should say something about this video. So this was done by, we had a, what shall we say, a very good engineering person who was coming to our labs and finding out about our research and actually did the captions for this video better than we could have done. And somehow this got into the public domain and it went viral on ACM and several places. And my students became actually local heroes. They were on local television for a day, etc. Okay. Now that was a test on a laboratory system, and it was actually important for us to do it there because all these equations about noise and so on are completely a figment of your imagination. Somehow it has to work on an actual system. Now, does it work in actual car? Okay. when the tire meets the road? And this is actually a very important question, because simulation models for vehicles, for cars, for process control, typically will capture the Newtonian dynamics. Okay, but they don't typically have models for the noise in the system. So there are no models for ambient noise. For example, what is the model for road noise in a car or tire noise? There are no models for that. Okay. So simulation models only model the deterministic part, not the random noise. However, our watermarking fundamentally relies on the ambient noise. Basically, the watermark hides in the ambient noise. And it relies on the fact that the attacker cannot separate the ambient noise from the watermark. Okay, so so we have to actually test this out in practice. So can we detect minute correlations of the watermark in the sense signals so that we can detect attacks in a timely way? So road noise plays a crucial role, and that's not modeled. So the test of the pudding is only in the tasting. So here we implemented this on a Lincoln MKZ, which has been opened up so that you can experiment with it. So this is an autonomous vehicle. And this is the architecture. Here's the autonomous vehicle. There are many types of sensors. During the courses of experimentation, I learned a new word. It's got two types of sensors. One are called proprioceptive receptors, sensors, which are basically internal sensors, and extraceptive sensors like LiDAR and things like that. And then these sensor measurements are processed. They're sent over a CAN or an Ethernet interface, and there is an electronics control unit, and they go back to this drive-by-wire system, which controls steers, brakes, acceleration, and so on. So this is the actual architecture of the autonomous car. And we had an attack on the yaw rate of the sensor. And the scan interface allows access to OEM measured or calculated information. So we basically be able to do our experiments. And okay, and we implemented this at the Rellis campus proving grounds, which is an old Air Force base that has been turned over to this campus, become a new an extension of our campus now. And actually, in this example, also, there's not much to see. There is an autonomous vehicle. It's going around in a circle. And you cannot see much. It's just that it gets attacked, and then after some time, you'll just find that it stops, okay? Nothing much is visible, which is the way it should be if you have a good defense. So that's it, okay? So the attack begins at 10 seconds, and it's caught. So if you look at the graphs, you find that the attack begins, and we applied several levels of watermarking. Even with very minute levels of watermarking, we could detect attacks. So basically, we don't degenerate the normal operation of the vehicle. Nearly instantaneous detection, and watermark magnitude can be pretty small. So this was the autonomous vehicle. Now, we have developed this dynamic watermarking technique as a general purpose defense for cyber-physical systems. So we want to show its applicability in several domains. And let me show you now an attack on process control systems. So this is the bedrock of the process industry, oil refineries, etc. And we took a prototypical process control system in our lab. This is a 2-tank system where water flows into the top tank, and from there it flows down into a bottom tank. And you want to control the level of water in this tank as well as this tank. So there are 2 outputs, 2 levels of the tanks, and you want to regulate them. And the control input is the flow rate. And the flow rate of the water is determined by the voltage that you apply to an electric motor. So this system has 1 input, voltage, and 2 outputs, the levels. And these levels are measured by pressure sensors at the bottoms of the 2 tanks. Now, however, the sensor measurements could be hijacked. So the what you get could be false measurements of the levels. And what is the purpose of this attack? It could be to cause an overflow of a oil refinery, which can be a pretty bad catastrophe, or underflow, etc. And what our attack detector is designed to do is, as soon as it detects an attack, we're going to drain out the system to prevent an overflow. Okay, so that's our safety measure here. Okay, so I'll show you the movie. So the system is just starting up. Okay, after some time, it will reach steady state. Okay, so now the system is kind of in steady state, almost. Okay, now it's in steady state. It's being well regulated, and now the attack will start. Okay, at some point. So the system is being well controlled. The two tanks are at their steady state. Now, in the absence of watermarking, you can see the overflow. Okay. So now we're going to switch on watermarking and try to prevent the overflow. So the system is just starting up. Okay. It starts up at time 40, I believe. Yeah. So now the system has started and it's in steady state. And at time 60, it gets attacked, I believe. That's the attack. And immediately dynamic watermarking catches it and drains out the tank to prevent overflow. Okay. All right. Now why is experimentation important? If you look at this picture here, you see this froth in the bottom tank. This is the noise in the level control sensors. Okay. And our watermark has to penetrate through this froth and be detectable by signal processing. So that's something that MATLAB simulations cannot tell you anything about. You actually have to do this in practice. Okay. So watermark has to survive the froth noise. And this dynamic watermarking is fundamentally a stochastic approach. And simulation models, again, to re-emphasize, model only the deterministic part, not this froth noise. Simulation is not enough. So experimentation is essential to determining whether the method works. Okay, the last example I'm going to show you is an attack on the power grid. Now, this particular attack is not a real implementation because they won't let us anywhere near the real power grid and attack it. It's a simulation model. So you have to take all these results that I tell you now with a grain of salt. It's an attack on automatic generation control in power systems. So I'm going to show you how to attack the power system and how to detect the attacks. So what is automatic generation control? So basically, you can think of a power grid as divided into areas or zones. And each area, basically, you'd like the generation in that area to be equal to the demand. See, at all times in the power grid, the total demand has to equal the total generation. You cannot really store energy except you cannot store energy. If you generate too much power, the transmission lines may overheat and sag and things like that. You can store a little bit of energy in the inertia of the rotors, but that's about it. Okay. So you want a balance between generation and demand. And the power grid is broken up into areas. And you roughly want each area to be self-sufficient, but areas may help each other out. For example, if Houston has a very hot day, or lately a very cold day, then you'd like another part to provide it power. Unfortunately, in the case of week before last, it turns out that Texas is essentially decoupled from the rest of the country. They just have a 1 gigawatt line for obtaining power from the Eastern interconnection, I believe, which is not enough. So there was no way to share. But automatic generation control allows you to share power in a connected grid. Okay, and how is the sharing loop done? Okay, so here is one area. This is one area, and there's a bunch of generators in this area. Here's another area, a bunch of generators, and so on. So there are n areas. Okay. Now, the outputs of each of these areas are the powers and the frequencies. Now, the frequency nominally is supposed to be 60 hertz. Okay, so omega is supposed to be 60 hertz. But but if you're drawing too much power from a generator, then the generator begins to slow down and the frequency drops below 60 hertz. On the other hand, if you're not drawing enough power, the generator will speed up, omega will increase. So this frequency is used to determine whether you're in balance between demand and supply. So these are the variables which are measured. There is a network, and then there is a power sharing network here, okay? And you monitor all these power sharing, etc. And if you determine, and based on whether some areas, the frequency will be going down or up, the phase angles are leading or lagging, what you then do is you adjust generation. So this is a multivariable control loop. So if Houston is in deficit, we will increase the set point to the Houston generator, asking it to produce more power or less power. So it's a multivariable control loop. So basically, it's a multivariable control loop to balance demand and power at each of the areas. Now, in this particular case, okay, so that's there are several set points. And so AGC monitors frequency deviations and tie line flows across multiple areas and closes the loop with the generators. And it controls both the frequency deviations and the tie line power flows. The tie lines are these lines to share power. Okay? So ultimately, the goal of automatic generation control is to ensure that each area responds to its load changes appropriately. And it operates in the 20-second to 30-minute time scale. Now, how can you attack this? Well, for example, one easy way is to misreport this frequency. So nowadays, these frequencies are being measured by synchrophasers or phasor measurement units. And the frequency measurements are packetized and sent over. So somebody could just intercept some packet and then misreport the frequency. So even if the frequency is 60 hertz, somebody could tell you it is 59 hertz. And that makes the operator panic because now the system, he thinks, is demand is way greater than supply. So the operator may order load shedding. Or if the frequency is reported as high, then the operator may shut down some generators. So it can be attacked by under-reporting or over-reporting the frequency. And what is our watermarking detection method? We're going to add a small private injection to the set point, a small dither to the set point. Okay. So I have a few things to do. I have to show you that this dither doesn't affect the normal operation of the power plant. And I should also show you that this dither can then be used to detect attacks on sensors in this power plant. Okay, so that's the defense by dynamic watermarking. So this is a synthetic power system with 10 generators, 4 areas. And first graph shows you the operation of the system in the presence of watermarking and in the absence of watermarking. And basically you see that the behavior is almost the same. So watermarking doesn't really affect the normal operation. Okay. Now we're going to look at a destabilization attack on automatic generation control. And in this particular case, the attack is started at 18 minutes, I believe. Oh, sorry, attack is started at 10 minutes. So until 10 minutes, the system is fine. The attack is started at that time. But the operator only realizes that an attack has happened at 18 minutes. So the operator is watching the signal. And then when the frequency rises above a certain threshold, then the operator realizes that there's an attack. So it's 8 minutes late, okay? But with dynamic watermarking, as soon as the attack comes on, you can detect it instantly, okay? All right. Now this is a destabilizing attack, but you can actually have a more subtle attack, which doesn't quite destabilize. The attack is not severe. So the frequency is oscillating around and the operator is not quite sure if there's an attack, okay? And even in this case, dynamic watermarking will detect the attack as soon as it happens. All right, so that brings me to the end of the talk. I just want to make some concluding remarks. So cyber-physical systems are important for society and economy. And in fact, the 21st century will be the age of building large societal infrastructures all over the globe for advanced services in power, in water, in transportation, and so on. Okay, and a lot of future infrastructure will be cyber-physical systems, societally and economically important. And the security of this is a very rapidly emerging area. Basically, these cyber-physical systems will not be deployed unless you can give guarantees about security. Okay, so they're safety critical, and lots of attacks have already been demonstrated. And dynamic watermarking is a possibly general purpose defense for these systems. And there are many, many interesting problems, and there are lots of references, and I will stop there. Thank you.
Thank you very much, Professor Kumar, for an exciting talk. So we have few questions, and I'll actually call them in sequence. So I'm assuming, Ardhendu.
Mr. Zhao.
Yes.
I have to leave for a VCR meeting soon. May I ask a question first?
Yes, you can. And I'm asking, so Doug, Sid, and Ardhendu, do you have any time constraint?
Not from my side.
I would have to leave at around 11:15, but that's okay.
Yeah, okay. Okay, Genda, you can go ahead.
Okay, I have thank you for exciting presentation. I have a question regarding to the type of attack. If somebody knows your watermarking technique is in place in the dynamic system, and that person inject attack using kind of like a gradually increasing, not a one-time post kind of attack, is a more like over time accumulated attack. Would your watermarking technique be equally effective?
Yeah. Because as soon as, I mean, if it is so minute that it doesn't matter, then I don't care. The moment it has any effect, I'll catch it.
Well, the point is it possible that that person inject this kind of attack accumulate in a small amount each delta T that you will not be able to see, but
No.
if that attack scheme is very small, it can accumulate by itself over time to the point that will impact dynamic system.
Yeah, so this is exactly that kind of an attack. It's not a severe attack. It's kind of gradual, and it's done very delicately, just so that your operator is not sure. Okay, but watermarking catches it instantly.
Okay.
Okay. Yeah.
All right. Thank you.
Mm-hmm.
Good. So Ardhendu, you are next.
Thank you, Professor Kumar, for the nice talk. Actually, I met Bharadwaj when I was in Texas A&M for this summer school on information theory.
Oh, wonderful. Very good. Mm-hmm.
Yeah, actually, yeah. So, so very elegant approach. I like this sort of. It reminds me of this sort of similar things what people have been trying for computer chips, but there they are looking at some sort of physical properties of the chip exactly. But I digress. So in this particular case, when you're adding Gaussian noise, I mean, of course, the operator cannot. I mean, is the operator the one who is operating the actuators? Is he the one adding the noise, or is the noise addition mechanism can also be thought of as part of another automatically controlled cyber physical system?
Yeah, I mean that. So let's go back. Okay, so this is a signal that's automatically added to the actuation input. So in practice, it will be generated by some computer and added. Okay. Now, for this defense to work, this piece needs to be secure. Right. If somebody can intercept this piece, then I can't help you. So this part is secure. So that's basically what it takes. And it can be done. I mean, if it is a fast moving system, I would guess a computer would generate it. But in many process control system, your sampling rate could be 30 minutes. You may only sample the system every 10 minutes or 30 minutes. In that case, even an operator can add manually. But that's just mechanics, what's detail, implementation detail.
Got it. Yeah, I kind of figured that, because I mean, this is like an addition, like it's a watermark. So an attacker could always subtract it out if they had control of that.
Yes. So we are assuming that this piece of the system is secure.
Right.
Yeah.
And so that brings me so two things, very interesting things that you even showed in your real world experiments. One was the magnitude of the noise. So I guess the sigma square E. And the other was the one that you just mentioned about the sampling delay. So I imagine you have these two tests, right? One is checking the variance, the sample variance with equality with sigma squared W, and the other one with the addition of the two sigmas. So one thing is that it seems that you need to know the exact value of sigma W. Is that a reasonable choice? Because if you just had a upper bound on sigma W, it seems that you are saying that you need both the tests to be able to detect.
So now we're getting into how one uses theory in practice. So what you could just look at the level of the watermark, the level of the test, and if it suddenly jumps up, you know that there's something happening. Okay. So the question is, so at some trusted point, you have a level, and then if it suddenly jumps up, something else has happened. Now, I should tell you one thing. This will also catch sensor failures. Now, the question is it a sensor failure or is it or a malicious attack? Actually, it doesn't matter, because that's just a question of intent, right? Was there a hostile person involved or just accidentally it attacked? Right. And also the issue is, if the ambient condition has changed, then also it detects it. So it will detect any change essentially, okay? And whether it is hostile or not, that is up to you. Some further diagnosis needs to be done. So the system can also be applied for any change point detection of any kind. Yes.
Okay. And so just last question, like in change point detection, they often compare this likelihood ratio test, right? Between if they have a probabilistic model of how the outputs. But it seems here you're just dealing with the variance, which is very nice because you have like a very one line that, oh, we need 0 power if someone has to attack it successfully. But I wonder how does it compare against those, like in many?
No. Yeah. So the point is this. So, okay. So in the theory, okay, I'm writing this as a asymptotic test. I'm saying the long-term average of this should be this, and the long-term average of this should be this. And if they're not, then there's an attack, right? But this is a long-term average as t goes to infinity, right? So that's the theoretical. What it simply says is that the probability measure should satisfy those two properties. Now, this asymptotic test is very standard statistical test. You convert it to a threshold test, okay? And exactly what you said. So this threshold is a balance between false alarms and misses. So at that point, it becomes standard trade-offs between type 1 and type 2 errors and things like that. So all of that is routine, okay? And the operator can tune it. Where do you want to set the threshold? If you set it over here, you may get some false alarms. If you set it over here, it may be appropriate.
So Ardindu, you are done with your question, I guess, right?
Yeah, I'm done. Thank you so much.
So Sid, you are next.
Hello, Professor Kumar. Thank you for the talk. So one of the questions that I had as I was listening to your talk is, now how sensitive is your approach to time? Because sometimes attackers may only put in all their energy in one moment and then carry out whatever they wanted to, disrupt whatever they wanted to disrupt in that one moment and get out. So can you detect and intervene such attacks in such short periods of time? And or maybe are there any other attacks out there? So for example, I can introduce a constant into the system, to the system equation, and that doesn't change the variance. So there are ways that you can step out of this variance detection process. So I'm trying to understand, have you looked at the scenario?
Yeah. So the first point is, this goes back to somebody said, what if it's a gradual, mild attack over a long period? Or you're raising the other point, what if it's a huge attack over a short period, right? Either of them will change this long-term average. So basically the point is, if the attack is to cause damage, then if it's a mild attack, it'll have to be sustained.
Right.
But if you want to cause attack in a short period, it'll have to be massive.
Right.
But either of those will get detected. Because in order to inflict attack, you'll have to reveal yourself.
Right. But the question, would you be able to
now
detect?
The constant, you mentioned is constant. Okay, constant, yeah, constant is not a problem. In fact, the attack that we have on this this case, I think here we actually added a constant.
I see. Okay.
Okay. And even in the actual Lincoln Mark Z also we added a constant. Yeah. They get detected.
Okay. But the question that I had was, would you be able to detect it on time? Because whatever the attacker did,
Right.
it may have, his goal was to launch an attack
Right.
to momentary impact and not a long-term impact. But you're relying on a long-term average.
No. I mean, no, I convert that into a threshold, right?
Right.
So if it is, so the question of timeliness, so you see the sensor attack happens here, but it gets detected when you cross some threshold. And this is related to the sequential quickest detection test that was the previous gentleman was just asking, right? So, so there's a detection delay, right, between the attack of the sensor and this. Now, if it's a mild attack, it may be a longer delay. If it's a sharp attack, it will be instantaneous. So basically, the detection will be related to the magnitude of the attack you're able to cause.
Okay.
So it self-calibrates itself.
I see.
Yeah. So if you're trying to cause damage in a hurry, I'll catch you in a hurry. If you're causing damage slowly, I'll catch you slowly. But point is, you won't be able to cause too much damage. Ultimately, the test, though, is you have to look at the reality of it. So, for example, in this case, does it get detected in an actual car? Does it get detected in an actual actual tank? Ultimately, the test is in the eating of the pudding.
Yeah. I understand.
Yeah.
The second question that I had for you is maybe since you brought the car up, I'll add one more to the first question, and then so I am also working on a transportation test bed in my lab, and in fact, when you showed me that photograph, I was quite excited because we have a similar layout in place. One of the challenges that we have is, how did you even model those vehicle control equations?
We used kinematic equations. We didn't do dynamics.
I see. Okay.
So I think let me see. I think I may have described them over here.
Yes.
This is simple. So this is a simple unicycle model.
I see.
So basically, there's just a position and a heading.
Okay.
You can just think of it as a unicycle. Yeah.
I've noticed that. So your cars, what kind of sensors do you have in your test bed? Do they have anything like? So you said they're autonomous vehicles. I was wondering.
Yeah. So we have different things that you can use. For example, we have cameras on the roof. You can use, if you want to switch those sensors, you can use those as sensors, you can do that.
Okay.
Or we also have a Vicon system. You can also use that if you want. It's really up to you. This test bed is completely configurable. You tell me what sensor you want to put, and we can. In fact, we've even flown quadrotors in this space under the net. Okay. Yeah.
I'm trying to build a similar testbed right now as we speak with JetBots, which are robots released by NVIDIA, and each of those robots have their own cameras, so you can actually run some computer vision based algorithms to navigate them. And but the biggest question that we had was, how do we even model those equations, the control equations? And looks like kinematic equations is a great start for them, and I'll probably look into that.
Yeah, I don't know. Yeah, I don't know about those.
The second question that I had was, now since we're talking about attacks, now if you look at most of the security threats that are out there, there are surveys that have been done by cybersecurity companies. And there is this one report that talks about human decisions being socially engineered by these hackers, and that constitutes roughly about 90% of attacks out there. Now, your current work doesn't capture that at all because you've only focused on cyber physical systems. I was wondering, have you thought about cyber physical human systems where a human also is involved in the control, and how would these approaches, or have you thought about anything in that direction?
Okay, actually, I think it doesn't matter what the controller is. Okay, so let's take, let us take, which picture would be good? Okay, so let's take this car, right? In this particular case, we had an automatic autonomous vehicle, right? So the steering wheel was automatically being controlled based on the reported measurements, right?
Yes.
Now, but however, supposing you replace that with a human driver who's being given the same measurements. Now, how a human driver will process electronic measurements, I don't know. But supposing a human driver also could look at something on his or her iPad and control, right? Then the same theory would apply. It would apply in the same way. As long as you're making decisions based on certain sensors and those sensors are compromised, this thing will catch it.
Mm-hmm. I see.
Yeah. All it needs access to is the actual control input that you apply. It doesn't matter what control law caused that control to be applied. It doesn't matter.
Interesting.
You just need to know the signal UG, not G, not the control law. Okay.
Okay.
So I don't need to know your policy. I just need to know what you did.
Very interesting.
Yeah.
So CD, could you go to the next person?
Yes. Thank you.
You're done? Good.
Yeah.
So Doug, you are next.
Yeah, thank you for a very nice presentation, and thank you for indulging all of our questions. I see we're well past the hour.
Pleasure.
Maybe I'll hold it to one question in the interest of time. So a lot of the reason we're using feedback control, right, is system uncertainty. I would guess that when we start bringing uncertainty, you didn't discuss this explicitly, but when you start bringing that in, that starts to create thresholds on your ability that might be able to map. If I have so much system uncertainty in my process that I can't detect, until it's above some threshold of malfeasance or something. Is that the case, or do you have any thoughts about how to extend the theory in that case?
Yeah, that's a very good question. I think so. This is a model-based defense, right? Because I'm using. I guess your background is control, right? Yeah. So you're talking of, say, unmodeled dynamics and things like that, right? So this is a model-based defense, and I'm using the nominal models in my attack detector. Okay. So it turns out that there's two ways to look at it. In a safety critical system, right? People will actually model the plant very well. Okay. So that knowledge is there. The other way to answer this question is, we're looking here at an actual automobile. which has all these issues that you mentioned on model dynamics, etc. And it works in spite of all of that. And that's the reason it also works on this actual process control, which has actual model dynamics.
Well, this is a good example, right? So what if it's a windy day? Does the car think it's under attack?
Oh, as I said, yeah. So okay, so suddenly if there's a gust of wind, which is unexplainable, it can assume that's malicious. But however, supposing the windy day has been going on and it settled to a new normal, and then it suddenly jumps, then something. Basically, it is catching changes.
Okay. So you might have kind of
unexplained changes. Yes.
Yeah. Okay. Okay.
So you may get false alarms when things change, but the point is that an attack will not go undetected. So if it errs, it'll err on the size of caution. Yeah.
It's a very nice, simple foundation, right? That you can begin to at least approach a lot of these questions with.
Right.
Very interesting.
Thank you.
Thank you.
Sajal, you're muted.
Yes, I was muted.
Yeah.
So Doug, do you have any other question or you're done?
No, I'll pass on my second in the interest of time.
Good. So Johnny, you are next. Johnny, are you still there?
Yes.
Okay.
Oh, yeah. Thanks, Dr. Kumar. So wonderful mathematical solution for the attack detection. So I think could you elaborate a little bit? I think you mentioned that the magnitude of the watermark actually doesn't matter too much. I think in one of the example, you also mentioned that you can detect attack 7 minutes early. So I just wondering whether you can elaborate a little bit more on the watermark input, such as magnitude, on your response time, and also on your control energy.
Yeah, so clearly in theory, there is a trade-off between the magnitude of the watermark and the detection delay, right? So there is a trade-off. If the watermark is 0, then the detection delay is infinity. If the watermark is infinity, the detection delay is 0, right? So there is a trade-off. The real question is, how big is that trade-off in practice? What is that range? And all these experiments are to show you that in practice, it is pretty fast. Okay, so all I can tell you is that we tried different watermark and it catches it practically pretty quickly. In the power system, you saw this in the water tank business. It immediately drained the tank, right? It didn't let it overflow. So the detection delay was fine. And you saw it in this power system example, which, however, is only a simulation example. So here you see that it catches it very much actually the next sample. So the practical answer is, in this particular case, the trade-off is well within the bounds of what we would like. So the detection delay is short enough that it is fine. But in theory, there is a trade-off, yes. In practice, this trade-off is acceptable in these systems.
So Johnny, you are done? Okay. So next question is from Ethan. Ethan.
So you've got a lot of examples of this working on systems that need to tend towards some constant value, like your water example. Does it work well on systems that don't need a non-constant value? For example, like an autonomous car needing to make a sharp turn to continue staying on the road? Or is that something you would need like multiple different versions of this that operate under different expected conditions for it to succeed at detecting attacks? And
no, actually, in the power system case and in the water tank case, they were a constant level, but not in the case of this laboratory collision avoidance system, right? That was going all over the place. It's one car is following another, right? So that doesn't matter. Yeah, it's going all over the place. Yeah, so it works. It doesn't need to be a set point control, if that's what you mean. It can be an arbitrary reference trajectory for tracking.
Awesome, thanks.
Okay.
Okay. So I think, thank you very much, everyone, for all sorts of nice questions. So Professor Kumar, I have one quick question. You have already spent quite a lot of time. So sometimes, especially when you look at it, because you have the physics-based model, and on top of that, the sensing and cyber domain, right? But if you look, sometimes you have the time series data, which are completely as data-driven analytics that you're doing. And we have done similar things on smart grid and some on transportation, right? So if there are a lot of fluctuations, so sometimes the variance may not actually capture everything. We have to go for higher moments, right? Have you looked into any of these systems where the variance is not able to capture any, let's say, threats or attacks or any of these things, but you have to look into higher order statistics to capture anything which means something significant?
Okay, so I guess you're asking a very subtle question. You're talking of non-Gaussian noises, right?
Right.
That's what you're talking. Yeah. So,
right.
So first of all, we actually have a huge contract with the DOE to protect the distributed energy infrastructure of the US. Okay, and we are the lead, and we have several universities involved, including Illinois Institute of Technology, which has a very nice microgrid, and MIT, and we have companies. We have Argonne National Labs, DOE, etc. So we're trying to actually protect that. Now in those kind of systems, so in systems where you may not have a model, we can do system identification. So we can run another loop for system identification, integrate it into this thing, and build a larger attack detection system. Now, coming to your non-Gaussian case, yeah, so we actually have a theory for non-Gaussian. I just had one slide on it. It turns out that the non-Gaussian case is quite a bit more difficult, but we can characterize necessary and sufficient conditions to catch attacks in the non-Gaussian case.